It is IChO 2023, and we have problems 29 and 30 about pericyclic reactions. 29.1, question number 1, asking how many electrons in diarylethane A, which are directly involved in the photochemical occurring electrocyclic ring closure to form B. And the answer is 6 electrons. And I'm showing them with the circles. So there is a trick that you need to understand, that you need to rotate around the sigma bond all your those parts with sulfurs so that they can give you the product B. It's easy because product B is given to you. But then what you should realize is that you are forming a six rings cycle, and that's why you need to put to form a sigma bond between those two, and overall you are using 6 electrons. That's very easy. Then the next question is also easy. In what sense do the methyl groups of the diarylethane have to move according to the Woodman-Hoffmann rules when B is formed? And that's kind of technical question because the table is given, so you need to take a look on into that table. Your 6 electrons correspond to 4n+2 rule, and the conditions are given. It's a photochemical reaction, so that's why it's conrotatory motion. You can arrive to the same conclusion just by analyzing the product and the way orbitals move. Or you can take a look on the table, it's much easier. Then draw the products D and E of the hypothetical thermal allowed cyclization and the photochemical allowed cyclization of compound C with the correct relation configuration. And the thing is that when you have electrocyclization, both light and heat are allowed by the symmetry. It is just one will be conrotatory, another one will be disrotatory, and that's why you will have different stereochemistry for the product. So here you can either memorize what will be the product, or you can do the analysis yourself, again showing the orbitals, thinking the way they are moving, and also thinking where would the methyl group go. And you will arrive to the answers shown here. The next question is kind of linguistic, so sometimes you can have a feeling that you are at the linguistic Olympiad, or at least you are asked something that you must know by heart, some definition. And why I'm calling it linguistic, because we usually have terms from Old Greek or ancient Latin language, like here. So choose the stereochemical relation between the resulting structure D and E, and those are diastereomers for sure, because you see that we have 2 chiral centers and we just change one configuration, so they are not anyhow mirror of each other, they are not enantiomers, but they are diastereomers, and also they are epimers. And I would forget this term, so I remind you that it means 2 isomers which configuration is different in one of the centers. So that's what we have here. Here and in that place we have different configuration. So that's why they are epimers. But they are definitely not constitutional isomers, which means that there will be some interchange of atoms whether the formula is the same. And they are not conformational isomers because they are stereo isomers. Conformation will be having basically the same structure, even the stereochemistry, but changing the conformation, like rotating the bond. So state how many products could be expected under thermal and photochemical conditions in the case if R is ethane, and that makes some difference. If we would have methane group here and here, then due to the symmetry of the molecules, some of them will be all the same. But because we have on the left methyl group, on the right ethyl group, this the first and the second are not the same. And overall, we can have 4 classical isomers, a pair of diastereomers, a pair of enantiomers. The next question, choose the stereochemical relation between the products formed in the photochemical ring closure when R is equal to ethyl group. And yeah, so I think maybe I'm mistaken. So we have photochemical, right? And we will have something like this. And if we rotate in other direction, we should get this product. And those should be enantiomers. Huh. Who knows by heart whether they are diastereomers or enantiomers, the third and the fourth, and why? Maybe I copied the wrong answer. I think they should be. Yeah, let's just. Yeah, they are a mirror of each other. They should be enantiomers. So this you can also check a bit later. And this is the next question. The problem number 30 is much longer. So it's about the synthesis of vitamin B12, but there are some questions about the pericyclic reactions. And the first two are like this. So give us the structure of intermediate from A to E. We're not going to do that, but we would like to focus on the very first steps here when we put two reagents together, and then there will be a pericyclic reaction from A to B. And we need to explain what is the role of reagent SN chlorine 4. And that is an advanced question because it's not really obvious what is this SN chloride is. However, what we should understand is that we need to put another reagent here, and then we will get the molecule B, and this is a pericyclic reaction. And here I'm giving another pericyclic reaction which is somewhat similar to what we have in the problem, and you can see here that this is an acid, and that could be nothing, or it could be iodine, SN chlorine 4, titanium chloride, zinc chloride, BF3, and chlorine 3, aluminium chloride. So for BF3 you should understand how it works, because BF3 will be a planar molecule with a empty orbital, and it will definitely be an acid. The same applies to aluminium chloride. But SN chlorine 4 doesn't seem to be a Lewis acid. At least you would not see any MO orbital there, empty. However, what is interesting is that SN chlorine 4 is eager to be an acid, is eager to get some lone pairs, and this is somewhat due to the size effect. Like C-chlor4 and silicium chlor4 will not be able to form more than 4 bonds because they are quite small. They will be completely surrounded by the chlorines, with a SN chlor4 is the tin is quite big atom inside, and it would like to have higher coordination. So it will form complexes like SN chlorine 5 as SN chlorine 6 with 2 minuses, of course. It will get some bases inside. In here, it will form a donor-acceptor bond with oxygen. And that is what is meant in this problem. It will act as a Lewis acid. It's just FMO theory will also tell you that's acid, but it's not so obvious to see in the molecular orbital picture. Anyway, it will be giving a bond here. So taking the lone pair, and that lowers the LUMO orbital. What does it mean lowers? Well, whenever you delocalize something, so it will participate in this conjugation here. And whenever you delocalize, it will go lower in energy. Maybe it's a too bold statement, but yeah, at least here it will be lowering. And now you should remember that suppose you have a very high LUMO, it's somewhere very high in energy, and you have this isoprene with low HOMO. By lowering the LUMO, you will put them closer to each other, to the same level. And I highlighted that whenever they come closer, the stabilization will be maximized. So that's what we are gaining here. By lowering the LUMO, making it, well, the true answer will be that we don't only lower, but we are lowering to the same level as HOMO, closer. We're making the gap between, we're making the gap between two orbital levels smaller so that the interaction becomes more stable. That's a long answer. Anyway, keep in mind that this is one of the ways to make your reaction happen thermodynamically and kinetically more favorably. And as Lewis acids, you can use also titanium chloride, zinc chloride, aluminum chloride. Good. And next, it was quite easy, but please do this exercise here. Derive, well, basically draw the molecular orbitals of octatriene as a model of the reaction discussed in the problem. And it doesn't matter how we draw the geometry of that molecule. When we are doing the MO analysis, it will be all the same for us because the pi system is in the same plane. So it doesn't really matter whether we have E, Z, double bonds. What matters is that they are on the same line. So we will have all the same diagram. And again, I was talking that we start from the bottom and we do not have any nodal plane. Then we introduce one nodal plane, then we introduce two nodal planes, then we introduce three nodal planes between the orbitals, okay? And then we introduce 4 and 5, and that's how we create this MO orbitals. You will eventually understand that the third one will be filled because we have in total 6 electrons. Now the same we can apply to the analysis of the reaction itself. Now we have this MO diagram. We draw a spatial, a three-dimensional figure of our orbitals here. We focus only on HOMO, and what's most important, we only need the terminal orbitals here. And then we realize that in order to put them in phase to make a constructive overlap, we need to rotate them in different directions. So it is this rotation, this rotary. And that's it. That's how we create a sigma bond. And the same question was about now photochemical condition, because when we excite one electron to the next level, that is the former LUMO, and differently from the orbital below, it will have a different symmetry. So they are alternating. Remember that the first orbital will be always symmetric, antisymmetric, symmetric. Now we have antisymmetric, and that means when we have this three-dimensional diagram, we can see that in order to put them into the same phase overlapping with each other, we need to rotate them both clockwise. Actually, it doesn't matter whether you rotate anti-clockwise or clockwise. What matters is that you rotate both left and right orbital the same direction on the clock. Let's say clockwise here. And that's why we say that it is con-rotatory. Con means in Latin with. Another result, you can see that now we can definitely rotate also the methyl group in the same directions, and we will get the trans, I would say, yeah. So they will be pointing one front of us, another backwards. And there was another question in problem 25.4. We needed to analyze just this reaction here where you have a double bond reacting with another double bond, and it looks really frightening, but they are not asking about stereochemistry of all other groups here. What the point is only the stereochemistry of the within this left part of cyclobutane here. Well, we have 4-member cycle. And this is the simplest analysis we could do, stating that if we just, we now focus that we put 2 double bonds together, one on the left, another on the right. So we abstract, we simplify everything just to double bond. And if we take a look on the HOMO of ethane, then it is symmetrical, but LOMO is antisymmetric. So there is no way to have a constructive overlap. Therefore, thermal reaction is not happening. But if we photochemically activate the molecule, then the HOMO will become antisymmetric, and the LUMO of another reagent is also antisymmetric, and therefore we can make the cycle. And that's how we explain why photochemistry is needed here. With that, I will finish the presentation.